Hello, my name is Paul Cumming, and welcome to the University of Drilling. The University of Drilling teaches the profession of drilling, using a series of self-paced visual training videos suited for the newcomers within the industry, and those who want to learn drilling, but have not yet worked in the oil and gas industry. If you enjoy this video, please visit our website at www.universityofdrilling.com for additional videos and learning materials within the art of drilling. To understand drilling, you must first understand porosity and permeability. The model you are looking at represents individual sand grains within a rock, wherein the sand grains touch and support each other, but leave pore spaces within the sandstone. While fracking technologies are opening up new productible rock formations, historically, sandstone and carbonates, or limestone with large connected pore spaces, have been the preferred location for finding oil and gas. So while sandstone may appear to be solid, sandstone rock can have small spaces between hard sand grains that touch but leave spaces between the sand grains that provide a pathway for fluids or gas movement. Let's take a microscopic trip through a permeable rock to understand how fluid can move through rock. Porosity is the space or spaces within rock that can hold liquids or gas. Permeability is a connection between pore spaces that allow movement of liquid or gas from one pore space to the next, which can comprise connected pore spaces in sandstone or fractures through an impermeable rock like shale. Low permeability is when it is difficult to push fluid or gas through rock, and high permeability is when underground pressures can more easily force fluids and gases through rock pores and fractures. Pressures that push fluids or gases through permeable rock can be generated by expansion from the heat of the Earth's molten core, or the overburden, which is the weight or burden of the rock resting on top of the permeable formation, which squeezes the pressurized trapped fluids in rock pores or fractures. It is critical to understand that rocks have fractures and pores, or holes in the rock, that can be connected or permeable, and that fluids comprising oil, water, or gas can move through these connected pore spaces into the hole you are drilling. When liquids or gas escape uncontrollably from the hole you are drilling to the environment, it is called a blowout. Drillers must manage the natural holes and fractures in the rock, as well as the pressure that may come out of those holes and fractures. Using heavy drilling fluids, or what the drillers call mud, as well as blowout preventers, which are connected to casing cemented into the ground. Pollution and deadly gases can be released into our environment, the ocean, or groundwater systems if subterranean pressures are not controlled. Now that you appreciate the importance of controlling the fluids associated with permeability and fractures in rock, let's discuss drilling and casing a well, using simple terms and the drilling language. In the art of drilling, there are three basic steps, comprising 1. Drilling or boring a hole in the rock. 2. Casing or placing a steel pipe in the drilled hole. And 3. Cementing the casing in the hole. Each of these three steps, drilling, casing, and cementing, are repeated in the same sequence over and over again until the well is completed. Drillers often call boring or drilling making hole, and holding back pressurized gases and liquids within rock pore spaces or fractures with drilling fluid or drilling mud, until they can run a long steel pipe string or casing into the hole and cement the casing in place to permanently seal the pressurized liquids or gases within the rock pores or fractures. Drillers also like to say that drilling is turning to the right to remind everyone that the drill string should always be rotated clockwise, because the drill string is assembled with individual joints of drill pipe that use right-hand threads, which would back out or unscrew and cause the drill string to fall apart if turned to the left. When rotating the string to the right, drilling fluid or mud is pumped down the drill string to exit the jets on the bottom of the drill bit. Drilling mud holds back the pressures within the rock, lubricates rotation of the drill string, lifts rock cuttings from the hole we are drilling, and cools and lubricates the drilling bit. There are many types of drill bits that can be attached to the end of the drill string, but this particular drill bit is a PDC cutter bit, which stands for a polycrystalline diamond compact cutter bit. The bottom hole assembly, or BHA, that you see here comprises a drill bit and drill collars that are, as drillers say, being run in the hole. When drilling or turning to the right and making hole, thick and heavy drilling fluid, or mud, is used to pressure against the newly drilled borehole and prevent fluids from pore spaces in the rock from entering the hole you are drilling. Mud, or drilling fluid, is also circulated down the drill string to exit the drill bit and carry drill cuttings up the hole where they can be removed at the surface. The thick and heavy mud provides a hydrostatic pressure to prevent subterranean or formation fluids from entering into the well. But the mud is especially formulated to form what is called a filter cake on the wall of the wellbore that seals the wellbore and avoids formation damage that can be caused by mud entering the pores of the rock until steel casing can be cemented into the wellbore. Carrying out the three basic steps, drilling, casing, and cementing, separates the well into whole sections of differing diameter. When the total depth, or TD, for the whole section is reached, the drill string is rotated in place, and the mud is circulated to clean all the remaining drill cuttings from the well. Once the drill cuttings are carried from the hole by the thick mud, the hydrostatic fluid column of heavy mud keeps pressure on the rock to prevent fluid ingress into the borehole, while the casing is being run into the hole. Tubular steel joints, or casing, are assembled and run into the hole, where they will be cemented in place to protect weaker rock formations from the heavier mud needed to drill deeper rock formations, and to prevent water or explosive hydrocarbons from coming to the surface to pollute the environment, and to protect other permeable formations like groundwater formations used for drilling water. Once the casing has been run in the hole, as drillers say, it is cemented in place. To place the cement on the outside of the casing, between the casing and the rock borehole, or between present casing and previous placed casing, it is first pumped down the current casing string and then followed by a cement plug, or plunger-like piston, and more drilling mud, until the cement exits the casing and returns up the backside. In drilling terms, the cement plug is pumped until the plug bumps into the casing shoe, which is the end of the casing string where the plug stops. A one-way valve, or float valve, in the casing shoe, or end of the casing string, allows the cement to be pumped from the casing's end and prevent the heavy cement from re-entering the casing. Cement that flows out under the casing turns the corner at the casing shoe and travels up the space, or annulus, between the casing and the borehole it is within. Once the cement has hardened within the annulus, or space between the borehole or previous casing wall and the wall of the present casing, the three-step drilling process of drilling, casing, and cementing can continue. A drilled and cased section comprises a set of borehole and casing diameters that are cemented together, but the next drilled and casing section will be a smaller diameter to fit through the inside diameter of the previous casing. A drill bit and drill string with diameters suitable for fitting through the previous casing and capable of drilling the next hole section is then run in the hole. First, the drill string must be turned to the right to bore through the previous cementing plug, and any remaining cement is the casing shoe track. After drilling the casing shoe track, drilling new hole can continue to the next hole section total depth, or TD, where cuttings will be circulated out of the hole to prevent the cuttings from interfering with running the casing in the hole and cementing the casing annulus. The process of pulling the drill string out of the hole and using the mud to hold pressure on the borehole until the casing can be run in and cemented is repeated. Because the overburden or weight of the rock above a certain point increases as you drill deeper and the rock becomes hotter the closer they are to the Earth's molten core, the trapped pressures of liquids and gases trapped within the rocks increase the deeper you drill. Because rocks and groundwater formations are closer to the Earth's surface, geologically younger and less compact than older and deeper rock formations, they tend to be weaker than the compact, deeper formations, and hence will fracture when exposed to the pressures present in older, deeper, and the drilling mud for making new hole in deeper formations must also be heavier, and hence casing is placed to protect the shallower rock formations from the mud weight needed to drill deeper formations, and the pressures within deeper formations that could, if released into a shallower formation, cause an underground blowout that could waste valuable hydrocarbons or which could pollute, for example, groundwater formations. Accordingly, the process of first drilling, then casing, and finally cementing is repeated over and over again to protect the surface and underground environments, using ever heavier drilling mud and smaller drill string and casing diameters until the well's total depth, or well TD, is reached. As you can see, the basics of drilling are relatively simple. Using heavier drilling mud, you drill new hole, run casing, and cement the casing in place over and over again until the final well TD is reached. At the University of Drilling, we believe that learning does not need to be complicated. You learn each individual set of tasks and visually tie them together so that you can remember them easily. The tutorial you have just seen is the core video tutorial for all of drilling, and from each all other University of Drilling tutorials are based. If you understood the video just presented, you can learn how to effectively communicate with drillers, or you can improve your chances of starting a career in drilling, or improve your potential for promotion within the drilling industry. The University of Drilling offers various drilling tutorials, like this one, free of charge, but we also offer a commercial series of visual learning tutorials which can be used by individuals for self-paced study and testing, and which is administered to our resident PhD who has over 30 years of experience in the drilling industry, where an individual who successfully passed in the verbal examination receives a certificate from the University of Drilling. Thank you for watching our video, and we hope you leave your comments on our website.